Hello everyone and welcome to our next lesson. In this video, we will be discussing catalysis and catalytic reactions. Expect in this lesson that we will be deriving rate law equations for heterogeneous catalytic reactions. Let's begin. Before we proceed, we first must define what is a catalyst. An understanding of the properties of a catalyst would also help us understand how do we derive the rate law of a catalytic reaction. We define a catalyst as a substance that alters the rate of a chemical reaction by providing a different mechanism or pathway. Simply stated, a catalyst offers a different reaction pathway that gives a different value of the activation energy such that the reaction could either go faster or slower. A very important concept that we must remember is that a catalyst is not consumed in the reaction process. If a substance enhances the rate of the chemical reaction, but it is being consumed, therefore that is not a catalyst. That can be classified as a reactant. A catalyst does not affect the thermodynamic properties such as spontaneity and equilibrium. Therefore, if you have a non-spontaneous reaction, a catalyst will not help make that reaction become spontaneous. Okay? Always remember that catalysts only affect the kinetic side, but they do not affect the equilibrium or the thermodynamic side. Catalysts can only make reactions go faster or slower, but it cannot make the reactions break the laws of equilibrium. And finally, we can point out that negative catalysts do exist. When we say negative catalysts, these are the catalysts that instead of hastening or instead of increasing the rate of the reaction, it actually decreases or arrests the rate of reaction. Negative catalysts are also important in some applications wherein we want to control the rate of the reaction. But for the most part, we will be talking about positive catalysts. We have two general types of catalysis. We have homogeneous catalysis and heterogeneous catalysis. For homogeneous catalysis, the catalyst exists at the same phase as the rest of the reaction mixture. A typical example of that is sulfuric acid being applied in esterification or hydrolysis reactions. Other types of homogeneous catalysts are enzymes in biological reactions and organometallic complexes. Normally, these are in the liquid states, and the substrate is also either in the aqueous or in the liquid state. Basically, for homogeneous catalysis, there are no phase boundaries between the catalyst and the substrate. The second type, and the one which we will be more focusing on, is heterogeneous catalysis. In this case, the catalyst is often a solid, and it differs in phase from the rest of the reaction mixture. It could be the case that your catalyst is a solid and your substrate is a liquid or is a gas. A common example of that is palladium metal, the catalyst for hydrogenation, zeolites as catalysts for alkylation or isomerization, and vanadium oxide for oxidation, etc. As I have mentioned earlier, we will be focusing more on heterogeneous catalysis because this gives us a different approach to the design of reactors containing catalysts. The use of solid catalysts over a substrate of either liquid or gas also presents its unique difficulties. Remember that for homogeneous reactions, we can simply overcome the limitations of mass transfer by ensuring that the flow is turbulent or that there is sufficient mixing, such that the slower rates of mass transfer such as diffusion will not hinder our chemical reaction. The problem with heterogeneous catalysis is even though your flow is turbulent over your solid catalyst, there will still exist a boundary layer wherein diffusion is the main mode of mass transfer. We will be discussing all of the interactions between mass transfer and reaction as we go through this lesson. Here are some of the desirable properties of a heterogeneous catalyst. First is it should have a high specific area. That means that area per unit mass of catalyst is high or is maximized. That is because for heterogeneous catalysts, the reaction happens at the surface of the catalyst. So the more surface area you have, then the faster rate of reaction you will have. Also, if you have a higher surface area of the catalyst, there will be less chances of poisoning or instances wherein inactivating species are adsorbed into the surface of your catalyst. Next, we also want our catalyst to have high selectivity for our chosen reaction. We want our catalysts to have a high selectivity because we only want it to be catalyzing the useful reaction or the reaction that we want the most. A common example of this is we want our catalyst to catalyze the forward reaction, but we do not want the catalyst to also catalyze the backward reaction because that would mean that the reaction rate of the forward and the backward reactions will just be comparable. So there will be no appreciable formation of the product because the catalyst can also catalyze the backward reaction. Okay? Another trait that we want for catalysts is they should be easily recoverable. Oftentimes in processes, heterogeneous catalysts are in pellets form and in rare circumstances, they can be in powdered form. We typically want catalysts to be in either the pellet form or in the immobilized bulk form because by then we can easily recover our catalyst. If your catalyst is a very, very fine powder and you are placing that in a pool of the liquid substrate, then it would be very hard for you to recover the catalyst. And it is also possible that you would have losses in the catalyst, which is not ideal in the process. Next characteristic, your catalyst should be easily regenerated, and that is to reverse poisoning. Let us first describe what is poisoning in catalysts. Poisoning happens when an unwanted substance adheres or adsorbs to the surface of your catalyst. If that unwanted substance becomes very hard to remove from the surface of the catalyst, that means that your catalyst is poisoned. That is because you now have less surface area available for the actual desired reaction. If your catalyst is poisoned, we can normally do several things to have the poisoning reversed. We could either increase the temperature or we could purge your catalysts with inert gases and liquids. For the heterogeneous catalyst to be worth it to be regenerated, it has to be easily regenerated. That means that it can be regenerated at a lower temperature or it can be easily regenerated by the flow of a non-expensive inert gas, such as nitrogen or argon. And finally, for processes, you want your catalyst to be both inexpensive and readily available. Sometimes, catalysts can contain rare and very valuable metals such as palladium and platinum. As such, for a general use catalyst, we would want our catalyst to be widely available and relatively inexpensive. A common example of this is zeolites, wherein it is both readily available and inexpensive. So these are just some of the desirable properties of heterogeneous catalysts that we must consider whenever we are choosing a catalyst to help a reaction in a process. Next, let us discuss the mechanism of action of catalysts. How do heterogeneous catalysts work? For the simplification of the analysis of the mechanism of heterogeneous catalysts, we have here the 7 important steps encompassing both mass transfer and reaction in the catalyst. The reactants and products in a catalytic reaction undergo the following steps. The slowest of the steps dictate the overall rate of reaction. So we have the 7 steps. The slowest of these 7 steps would dictate our overall rate law. We will be discussing each of these steps in detail, but in brief, we have external diffusion of reactants from bulk solution to catalyst surface, internal diffusion of reactants from catalyst surface to the inside of the pores. Remember that catalysts are often porous to have a high specific surface area. Next is adsorption of reactants onto the inner surface of the catalyst. After that, we have the desorption of products from the inner surface of the catalyst, and then internal diffusion of products from the pores to the external surface of the catalyst. And finally, we have the external diffusion of products from the catalyst surface to the bulk mixture. Let's go through each of these steps individually. First, we have external mass transfer. Remember that for heterogeneous catalysis, mass transfer is a very important part of that process. Normally, we cannot neglect the effect or the contribution of mass transfer. For the external mass transfer, the rate of mass transfer is dictated by the flow conditions around the catalyst. Generally, we want turbulent flow to assure a convective mass transfer. As a review of your transport phenomena, we learned that convective mass transfer is far faster than diffusive mass transfer. So for external mass transfer, what we normally want is to have turbulent flow to assure that we have a convective mass transfer. If you remember, our rate of mass transfer is dictated by this equation. The rate of transfer of species A is equal to Kc, or the mass transfer coefficient, multiplied by the driving force of the transfer, that is Ca bulk minus Ca surface. Cab is the bulk concentration of A in the reaction mixture, and Cas is the concentration of your reactant A at the surface of the catalyst. This follows the general form of our rate equations, and that is driving force over resistance. Our resistance in this case is 1 over Kc. As we have previously learned, mass transfer will be slowest in the direct vicinity of the pellet where a boundary layer forms. Remember that the boundary layer cannot be removed, it can only be minimized. So for highly turbulent flows, your boundary layer thickness, which is del in this case, would be very, very thin. And if you have laminar flow, we can expect that the thickness of the boundary layer would also increase. The reason why we normally want turbulent flow around a catalyst is to ensure that the boundary layer thickness is small, such that the mass transfer in the boundary layer thickness is by diffusion, wherein Kc, or the mass transfer coefficient, is equal to the diffusivity dAb divided by the boundary layer thickness del. As you can imagine, as your boundary layer thickness decreases, your mass transfer coefficient increases. That is it for the first step, external mass transfer. Now, throughout this process, we will be tracking the progress of two species, that is A, our reactants, and P, which is our product. So now, your reactant A is already on the surface of the catalyst. The next step would be internal mass transfer, wherein your reactant A would now attempt to diffuse to the inside surface of the catalyst. The rate of mass transfer inside is dictated by the size of the catalyst pellet and the surface concentration of the diffusing species, such that the rate of internal mass transfer is equal to K sub R, or our mass transfer coefficient for the internal diffusion, multiplied by concentration of A at the surface. Now, normally, this rate equation should have a driving force. The driving force in this case is the difference between the concentration of A at the surface minus the concentration of A at the middle of the catalyst pellet. Now, we will be assuming that the concentration of A at the middle of the catalyst pellet is almost equal to 0. And that is because of an assumption that as soon as A is adsorbed to the inside surface of the catalyst, it is immediately transformed into the product, such that the concentration of A at the middle of the catalyst pellet is very, very small in comparison to its concentration at the surface. We have here the relationship concentration of A at the surface is greater than the concentration of A at the center of the pellet. Therefore, this becomes CAS minus 0. Therefore, we always have the maximum driving force. That gives us this simple equation for the rate of internal mass transfer. Okay? This assumption is only valid if we say that the rate of reaction is far faster than the rate of internal diffusion. Next step, after the internal mass transfer, we now have the adsorption of your reactants to the inner surface of the catalyst. The rate of adsorption is dependent on the number of vacant active sites and is assumed elementary. Consider the adsorption and desorption of species A, which is our reactants, on an active site theta. Although this step is not the chemical reaction step, we will be representing them in terms of chemical equations for simplicity. Now, before we proceed, it is important that you think of the inner surface of the catalyst as a rough surface containing what we call active sites. The reaction can only happen in these active sites. Therefore, if your primary reactants cannot be adsorbed into the active sites, then the catalyst will not work. Okay? That is our assumption for the rest of our examples. Going back, we have here the reactions depicting the adsorption and desorption of your reactant A into a vacant active site. A vacant active site can be represented by theta V. The V is telling us that it is a vacant active site. So when our reactant A approaches a vacant active site, it is adsorbed into the active site. Therefore, we form the active sites with an adsorbed A. You can take a look at this diagram for clarification. So we have our reactant A and our vacant active sites. And when they combine together, we have our reactant A adsorbed into our vacant site. Okay? This is A, this is theta, and this is theta A. Now, since this is an equilibrium process, this has to be a reversible reaction. The reverse reaction of the adsorption is the desorption. The desorption process is simply you have the active site containing A, that is theta A, and that yields your active site that is now vacant, that is theta, plus your reactants A. Okay? We can now write our equilibrium rate of adsorption as the specific reaction rate for adsorption, that is K adsorption, multiplied by the concentration of A, multiplied by the concentration of the vacant sites. Remember that these reactions are assumed to be elementary. And then for the next term, we include our desorption rate, that is minus the specific reaction rate for desorption, that is negative adsorption, multiplied by the concentration of the active sites with adsorbed A. And since this is a reversible reaction, we can define an adsorption equilibrium constant Ka, which is defined as the ratio of the forward reaction rates over the backward reaction rates. This is the same concept as the equilibrium constant Kc. As an exercise, let us derive the equilibrium rate of adsorption, which includes our adsorption equilibrium constants and a mass balance on the active sites. I have copied here our elementary steps and our equilibrium rate of adsorption. So let us now incorporate the definition of the equilibrium constant for adsorption. If we factor out the specific reaction rate constant in our rate equation here, we would have K adsorption times concentration of A times concentration of theta V, specific reaction rate constant for desorption over the specific rate constant for adsorption, multiplied by the concentration of theta A. Now, substituting our definition for the equilibrium constant of adsorption, we now have our rate of adsorption written as specific reaction rates constant for adsorption times concentration of A times concentration of theta V minus the concentration of theta A divided by our equilibrium constant for adsorption. At this point, we can also incorporate our site balance. Our site balance is all of the total active sites is equal to all of the vacant active sites plus all of those active sites with adsorbed A. Using our site balance, we can express the concentration of our vacant site in terms of the total concentration and the concentration of those with adsorbed A. We will be substituting this into our expression here along with another assumption of equilibrium. So at equilibrium, the overall rate of adsorption is equal to 0. That gives us our simplified equation concentration of A times concentration of theta V is equal to concentration of theta A over KAD. Substituting our simplified site balance, we have concentration of A multiplied by the concentration of the total active sites minus the concentration of those adsorbed with A multiplied by K adsorption is equal to theta A. Let us solve for the concentration of the active sites with adsorbed A. This becomes K adsorption, concentration of A multiplied by the concentration of theta T minus KAD, concentration of theta A times concentration of A is equal to concentration of theta A. Rearranging the terms, we now have K adsorption, concentration of A, concentration of the total active sites is equal to the concentration of theta A times K adsorption, concentration of A plus 1. A further simplification gives us the concentration of the active sites with adsorbed A is equal to K adsorption times the concentration of A times the concentration of the total active sites divided by K adsorption, concentration of A plus 1. This is now our expression for the equilibrium concentration of the active sites with adsorbed A. We will be using this expression in conjunction with the other steps as we derive the overall rate law. Let's go back. So we are done with adsorption to the surface of the catalyst. Let us now have step 4 or our most important step, and that is the surface reaction step. Surface reactions vary in mechanisms, and the type of mechanism will dictate the rate equation for the reaction. We will be discussing the 3 most common mechanisms for surface reaction in heterogeneous catalysts. First, we have the single site reaction. By the way, these mechanisms will only differ on the way on how they proceed with surface reaction and adsorption. For single site reaction, the adsorbed reactant reacts on the active site only, yielding the product adsorbed on the active sites. This is common in isomerization reactions. Consider the hypothetical isomerization reaction A yields B. This is a reversible reaction. Our single site reaction mechanism says that A or our reactants adsorbed on an active surface will react to form B, our product, which is still adsorbed on the active sites of the catalyst. This is our primary reaction. And of course, this being a reversible reaction, the reverse of that should also be considered. That is theta B or an active site with adsorbed B reacts to form theta A or an active site with adsorbed A. For these 2 elementary steps, we can write our rates of surface reaction as Ks or the specific reaction rate constant for the forward reaction multiplied by the concentration of theta A minus K negative S or the specific reaction rate constant for the backward reaction multiplied by the concentration of theta B. This rate equation for surface reaction can be used in conjunction with our earlier derived expression for the concentration of theta A. We can simply substitute that here and then solve the rates of the reaction. The single site reaction mechanism is the simplest heterogeneous catalytic mechanism. Let's have the next one. For the second mechanism, we have the Langmuir-Hinshelwood kinetics. This is also called the dual site kinetics because this involves the interaction between 2 adjacent active sites. One is taken and the other is free. Consider this decomposition reaction A yields B plus C and it's a reversible reaction. We can write the elementary steps as first, an active site containing A plus a vacant active site yields an active site containing B plus an active site containing C. You can think of our decomposition reaction as a splitting reaction wherein A is being split into B and C. And for that to happen, both B and C should still be adsorbed into active sites. So therefore, since we have two active sites on the product side, you also need to have two active sites on the reactant side. One contains A and the other is a vacant active site. And of course, the reverse of this reaction is theta B plus theta C yields theta A plus theta vacant. The Langmuir-Hinshelwood kinetics also describes the equations of the form A plus B yields C or A plus B yields C plus D. Basically, any reaction with either two reactants, two products, or both two reactants and two products can make use of the Langmuir-Hinshelwood kinetics. Okay? In some complicated cases, the Langmuir-Hinshelwood kinetics can also be used to describe the mechanism for catalysts with two different active sites. Two different active sites meaning that one of the reactants should adsorb into one of the active sites while the other reactant should adsorb to the different active sites. In this case, we are representing the difference in the active sites with the use of the prime. So theta is different from theta prime. Okay? If you want, you can use a different Greek letter to denote a different active site. And finally, the third mechanism is called the L-Rydell kinetics. In this mechanism, a free gas phase species collides with an adsorbed species. Consider the reaction A plus B yields C, another reversible reaction. Now, for this to become an L-Rydell reaction, one of the reactants should be adsorbed on an active site and the other should be a free species. In this case, A is adsorbed onto an active site while B is a free species. So what happens is B collides with theta A and that results to the formation of C, which is still adsorbed in the active sites. For the second elementary reaction here, we are simply stating the opposites of our previous reaction. The L-Rydell kinetics is often used for gas phase reactions wherein one of the reactants has a higher adsorption affinity for the catalyst than the other reactants. Okay? So please keep in mind those three different mechanisms. The three different mechanisms will give you three different overall rate law equations. And it is important that we know from equations and from graphs how to determine which mechanism do we have. We will be showing this in an example later. But first, let us go to the fifth step, which is desorption. So at this point, you can imagine that your reactant A has traveled from the bulk solution mixture to the external surface of the catalyst, and it has diffused to the inner surface of the catalyst, and it has adsorbed to the inner surface area of the catalyst where it has already reacted. That summarizes the four previous steps. Now it is time for your product to leave the catalyst surface. The desorption step is when the adsorbed product gets released into the reaction mixture. So for our hypothetical reaction A yields C, wherein C is our product, we now have here an active site containing C, and that undergoes desorption to yield free molecule of C plus a vacant active site. For this reversible reaction, again, we can write the net rate of desorption as small kd, or the specific reaction rate for the desorption, multiplied by the concentration of the active site containing C, minus the specific reaction rate for the reverse of the desorption, which is adsorption, multiplied by the concentration of the free molecules of C, times the concentration of the vacant active sites. At this point, you can also introduce the equilibrium constant for desorption, that is capital K sub D, just as what we did on the adsorption step. Now, some important things to note that the rate of adsorption and desorption for any species are the same in magnitude but opposite in signs, which should make sense because adsorption and desorption are basically the same rates but with different directions. Adsorption is towards the catalyst and desorption is away from the catalyst. Always remember that this expression is only true for the same species. For example, if you are talking about the product, that is species C, the rate of adsorption of C is equal to the negative rate of desorption of C. By the same token, the equilibrium constants for adsorption and desorption are also related by this reciprocal relationship. That is, the equilibrium constant for desorption for a particular species is equal to 1 over the equilibrium constant for adsorption of that same species. After this step, your products are now free from the catalyst. What is then left for your product is to leave the matrix of the catalyst. That is now steps 6 and 7. That is mass transfer out of the pellet, that is step 6, and mass transfer into the bulk solution, that is your step 7. These last two steps are simply the exact opposite of the first two steps. So we can revisit steps 1 and 2 for steps 6 and 7. The rates of diffusion of the reactants and the products may vary, due to their varying diffusivities with respect to the reaction mixture. That is the only difference between steps 1, 2, and steps 6 and 7. For steps 1 and 2, we are concerned on the diffusion of the reactants, while for steps 6 and 7, we are concerned on the diffusion of the products. Now, for a single heterogeneous reaction that could possibly have 7 different rates coming from 7 different steps, how do we know which of those rates would be useful in drafting our overall reaction rates? We shall first consider the reaction proper, assuming that the processes are not hindered by mass transfer. When we say the processes are not hindered by mass transfer, we will simply be neglecting steps 1, 2, 6, and 7. Therefore, we can focus on steps 3, 4, and 5. That is adsorption, surface reaction, and desorption. All the steps, when combined, would yield the overall reaction rate as assisted by the catalyst. At steady-state conditions, all the individual reaction rates are equal. That is, the overall rate of consumption of species A in our heterogeneous catalytic process is equal to the rate of adsorption, is equal to the rate of surface reaction, is also equal to the rate of desorption. This process is analogous to heat transfer with resistances in series because basically all of these processes are happening in series. And with that, the slowest process will dictate the overall speed of the reaction. For example, in our illustration here, if the surface reaction is very, very slow and the rate of adsorption and desorption are fast, that means that your overall rate of reaction will just depend on the rate of surface reaction because that is the rate limiting step. Always remember that our rate limiting step dictates the overall rates of the reaction. Okay, let us apply this with an example. We have cumene decomposing to form benzene and propylene according to the illustration here. So we have cumene adsorbing into an active site, and then the surface reaction occurs. In the surface reaction, you see that propylene gets separated from benzene, and the benzene is still adsorbed into the active sites. And then the final step is desorption, wherein the benzene is released by the catalyst. We want to determine the rate law, considering each of the 3 principal steps as the rate limiting. Therefore, we will have 3 different solutions. The first, we will be assuming adsorption as the rate limiting. The second, we will assume surface reaction as rate limiting. And for the third, we will be assuming desorption as the rate limiting. At low initial partial pressures of cumene, the initial rate of reaction is observed to be linearly proportional to cumene pressure. At high initial partial pressures, the initial rate of the reaction seems independent of the initial partial pressure. We will be using these 2 observations to determine which among our 3 different solutions is the correct solution, because there can only be one correct overall rate law. Okay, let's solve this problem. We have here our overall reaction C yields B plus P. For our adsorption step, we write our equation to be C, or cumene, plus a vacant active site yields an active sites containing cumene. Now, this is a reversible reaction, so therefore, we have the forward and the backward specific reaction rate constants. We can now express our net rate of adsorption as first for the forward reaction, that is the constant for adsorption multiplied by the concentration of cumene times the concentration of the vacant active sites minus the reverse reaction, that is K negative adsorption times the concentration of the active sites containing cumene. Doing what we did earlier, we can factor out our constants KAD, and then we will have the concentration of cumene times the concentration of the vacant active sites minus the concentration of the active sites containing cumene over our equilibrium constant for adsorption. This is now our expression for the net rate of adsorption. We will follow the same flow of solutions for surface reaction and desorption. Let us consider surface reaction. In this step, the cumene that is adsorbed on the active site decomposes to form benzene that is adsorbed into an active site plus propylene gas. Keep in mind that propylene was not adsorbed into an active site based on the illustration given. We have to turn this into a reversible reaction so that we can proceed with the analysis. Our forward specific reaction rate constant is small ks, while for the backward reaction, that is K negative S. We will be denoting S for the surface reaction. We can then write our net rate of surface reaction as small ks times the concentration of the active sites containing C minus small k negative s, or for the backward reaction rate constant, times the concentration of the active sites containing B times the concentration of free P or propylene. We can also extract our specific reaction rate constant for the forward reaction here and introduce our equilibrium constant capital Ks. We therefore write our net rate of surface reaction as small ks multiplied by concentration of theta C minus concentration of theta B times concentration of propylene over capital Ks. Capital Ks in this case is simply the ratio of the forward reaction rate constant over the backward reaction rate constant. This is now our expression for the rate of surface reaction. And finally, let's do the desorption part. For the desorption, this is simply the adsorbed benzene reacting to form a vacant active site plus free benzene. Remember that propylene was never adsorbed, so it does not need to be desorbed in this equation. Our forward reaction rate constant is Kd, and the backward is K negative D. We can then write our net rate of desorption as small kd multiplied by the concentration of the active sites containing benzene minus small k negative d times the concentration of the vacant active sites times the concentration of free benzene. As with adsorption and surface reaction, we can factor out the specific reaction rate constants of the forward reaction, therefore giving us our net rate of desorption written as small kd multiplied by the concentration of active sites containing B minus the concentration of the vacant active sites times the concentration of free benzene all over capital Kd. Capital Kd is our equilibrium constant for desorption. We now have our three governing rate law equations that describes the adsorption, surface reaction, and desorption of the reactants and products for the described reaction. The next part to our solution is to then consider each of these steps as the rate-limiting steps and deriving our overall rate equation. Let us start by writing our overall rate law. That is, the rates of consumption of our reactant, which is cumene, is simply equal to the rate of adsorption is also equal to the rate of surface reaction is also equal to the rate of desorption. If we assume that adsorption is the rate limiting step, we can therefore say that the rate of consumption of cumene is simply equal to the rate of adsorption. This being the case, we can simply copy our rate equation for adsorption from our previous derivation. That would be our K for adsorption multiplied by the concentration of cumene times the concentration of the vacant active sites minus the concentration of the active sites containing cumene over our equilibrium constant for adsorption. For us to complete this solution, we simply have to determine our expressions for the concentration of the vacant active sites and the active sites containing cumene. For these types of solutions, remember that our goal is to eliminate all of the concentration terms containing active sites. And for that, we simply have to gather the terms from the other two rate laws, the one coming from surface reaction and the one coming from desorption. By assuming that the adsorption step is the rate limiting step, we can then say that the ratio of the net rate of surface reaction divided by the specific reaction rate constant, that is small ks, is almost equal to 0. This is the same for the desorption. That would be rate of desorption over the specific reaction rate constant for desorption is almost equal to 0. That's because the specific reaction rate constants have very high values if they are not the rate limiting step. From our equation derived earlier for the rate of the surface reaction, if we set that to 0, we will now have the derivative expression, the concentration of the active sites containing cumene minus the concentration of the active sites containing benzene times the concentration of propylene divided by equilibrium constant for surface reaction is equal to 0. From this equation, we can now get the concentration of the active sites containing cumene, that is, active sites containing benzene, concentration of propylene, over the equilibrium constant for surface reaction. We need to set aside this equation for later. Next, for the desorption, our derived equation earlier stated that the concentration of the active sites containing benzene minus the concentration of the vacant active sites times the concentration of benzene over the desorption equilibrium constant is equal to 0. From here, we can derive our expression for the concentration of the active sites containing benzene. That is, vacant active sites multiplied by concentration of benzene over the equilibrium constant for desorption, capital KD. Now that we have all of these expressions, what's left to do is to perform the site balance. The site balance is a little bit different in this case because remember that we have several species adsorbed into the active sites. We have the vacant active sites, we have the active sites with cumene, that's theta C, we have the active sites containing benzene, that is theta B. Our site balance will be written as the total active sites is equal to the number of vacant active sites plus the number of active sites containing cumene plus the number of active sites containing benzene. We can now substitute our derivative equations coming from the net rate of surface reaction and net rate of desorption into our site balance. We now have concentration of theta T is equal to concentration of theta V plus the concentration of theta C is equal to concentration of theta B times the concentration of propylene over capital KS plus the concentration of theta B is equal to concentration of the vacant active sites times concentration of free benzene over capital KD. If you take a look at the second term of this equation, this is still expressed in terms of theta B. However, we can substitute theta B coming from our resultant equation coming from the desorption net rate. Therefore, we can write theta V times B times concentration of propylene over Ks times Kd. This is now our replacement for the second term of this equation. Now, at this point, if you take a look at our site balance, we only have two concentrations for active sites. We have the total number of active sites and we also have the total number of vacant sites. We can now extract the concentration of the vacant active sites. We will have the concentration of the total active sites is equal to the concentration of the vacant active sites multiplied by 1 plus concentration of benzene times the concentration of propylene over capital Ks times capital Kd plus for the last term that is concentration of benzene over capital Kd. This is now our final site balance. We can use this site balance to substitute this as an expression for theta V or the concentration of the vacant active sites in our overall rate law. The final steps of our solution would now involve substituting our expression for theta C into our overall rate law. And then if you take a look, theta C is still defined in terms of theta B. Therefore, we have to substitute theta B in our definition of theta C. And then theta B is now a function of theta V. So the last thing that we have to do is to substitute theta V both into the definition of theta B and into our overall rate law. At that point, there should be no more concentrations pertaining to active sites except the concentration of the total number of active sites, that is theta T. We can now write our net rate of consumption of cumene as small k adsorption multiplied by concentration of cumene times the concentration of the vacant active sites minus the concentration of theta C, that would be concentration of theta B times concentration of propylene over Ks. That is multiplied with the K adsorption at the denominator. But then we know from our previous equations that the concentration of theta B is equal to theta V times concentration of benzene over capital KD. We can now substitute this to our rate law. We now have net rate of consumption of cumene is equal to reaction rate constant for adsorption, concentration of cumene times the concentration of the vacant active sites minus theta B is simply equal to theta V times concentration of benzene. This is multiplied to the concentration of propylene all over capital Ks, capital K adsorption, capital K desorption. You can see in this equation that we can now extract our theta V. And remember that the concentration of the vacant active sites is equal to the concentration of the total number of active sites divided by 1 plus concentration of benzene and concentration of propylene over Ks Kd plus the concentration of benzene over Kd. Factoring out theta V and substituting, we now have our overall rate law for the consumption of cumene is equal to K adsorption multiplied by the concentration of theta T all over 1 plus concentration of benzene, concentration of propylene over capital Ks times capital KD plus concentration of benzene over capital KD multiplied by concentration of cumene minus concentration of benzene, concentration of propylene over capital Ks, capital K adsorption, and capital K desorption. And from here, it's just a matter of simplifying these expressions. We can start simplifying inside the parentheses wherein this expression could simply be equal to a common denominator of capital Ks, capital K adsorption, and capital K desorption multiplied by concentration of C times Ks, K adsorption, and K desorption minus concentration of benzene and concentration of propylene. We now have our net rate of consumption of cumene written as K adsorption times the concentration of the total active sites multiplied by the concentration of cumene, K adsorption, K surface reaction, K desorption, minus concentration of benzene and concentration of propylene. In the denominator, if we multiply the two denominators, we can simply have Ks, K adsorption, K desorption, plus concentration of benzene, concentration of propylene, times K adsorption, because we simply cancel Ks and Kd. And then for the final term in the denominator, we have concentration of benzene multiplied by K adsorption and K surface reaction. This is now our overall rate law equation for the decomposition of cumene forming benzene and propylene if we assume that adsorption is the rate limiting step. We have to go through two more rounds of this derivation because we still have to assume that surface reaction is the rate limiting and desorption is the rate limiting. Okay, so let's hold on to these results for now. Let us proceed to the assumption that surface reaction is rate limiting. This time, we say that the net rate of consumption of cumene is equal to the net rate of surface reaction, which we have determined earlier to be equal to small ks multiplied by the concentration of the active sites with cumene minus the concentration of the active sites with benzene times the concentration of propylene all over capital Ks. For this part of our solution, we can also say that the ratio of the rates of adsorption with regards to the specific reaction rate for adsorption is almost equal to 0 because of the large value of the specific reaction rate. Therefore, we now have the expression concentration of cumene times the concentration of the vacant active site is equal to the concentration of the active sites containing cumene over the equilibrium constant for adsorption. Coming from this equation, we now have the expression for the concentration of the active sites containing cumene, that is equilibrium constant for adsorption times the concentration of cumene times the concentration of the vacant active sites. Next, for the desorption side, we then say that the rate of desorption divided by the specific reaction rate for desorption is equal to 0. This gives us the expression the concentration of the active sites containing benzene is equal to the concentration of the vacant active sites times the concentration of benzene divided by the equilibrium constant for desorption. At this point, we can now perform the site balance. Our site balance for this is theta T, or the total active sites, is equal to the vacant active sites plus those containing cumene plus those containing benzene. We can now substitute our above equations. We will have total active sites is equal to vacant active sites plus theta C is simply K adsorption, concentration of cumene, concentration of the vacant active sites, plus theta B is equal to the concentration of the vacant active sites, concentration of benzene over capital K D. Similar to what we have done earlier, we can now extract theta V, or the vacant active sites. We have 1 plus K adsorption, concentration of cumene, plus concentration of benzene over capital K D. We now have the expression for the concentration of the vacant active sites as the concentration of the total active sites divided by 1 plus K adsorption concentration of cumene plus concentration of benzene over capital K D. Similar to what we have done earlier, our plan of attack would simply be substitute the expression for theta C or the active sites containing cumene, substitute theta B or for benzene, and then afterwards we can now substitute the definition of theta V into theta C and theta B. After that, we should be able to obtain the net rate of consumption of cumene if we assume that surface reaction is rate limiting. Here is our overall rate law. We have the net rate of consumption is equal to small ks, this is for the surface reaction, multiplied by the concentration of the active sites containing cumene, that is K adsorption, times concentration of cumene, times the concentration of the vacant active sites, minus the concentration of active sites containing benzene, so that would be concentration of the vacant multiplied by concentration of benzene times concentration of propylene all over capital Ks times capital Kd. At this point, we can now substitute our expression for theta V. From the previous page, our concentration of the vacant active sites is equal to the concentration of total active sites all over 1 plus capital K adsorption times concentration of cumene plus concentration of benzene over capital Kd. Substituting, we now have net rate of consumption of cumene is equal to small ks times K adsorption times concentration of cumene times concentration of the total active sites divided by 1 plus K adsorption concentration of cumene plus concentration of benzene over K desorption. This is for the first term of the rate law. Minus, for the second term, we do the same. This is the concentration of the total active sites, concentration of benzene, concentration of propylene, all over capital Ks, capital Kd, multiplied by 1 plus K adsorption, concentration of cumene, plus concentration of benzene over capital Kd. Further simplification would lead us to the net rate of consumption of cumene is equal to small ks multiplied by the concentration of the total number of active sites. We simply factor that out. Multiplied to, we can use the common denominator 1 plus K adsorption, concentration of cumene plus concentration of benzene over capital Kd. In the numerator, we have K adsorption, concentration of cumene, minus concentration of benzene times the concentration of propylene divided by capital Ks, capital Kd. This is now our net rate of consumption of cumene, assuming that surface reaction is rate limiting. So far, we have obtained two rate laws, one by assuming that adsorption is rate limiting. This second one was obtained by assuming that surface reaction is rate limiting. And let's do the final one, which is assuming that desorption is rate limiting. I have here our net rate of desorption as derived earlier, and that is equal to the net rate of consumption of cumene if desorption is rate limiting. Therefore, we can say that the rate of adsorption divided by the specific reaction rate constant for adsorption is equal to 0, and that is the same with surface reaction. From these generalizations, we have the following equations. First, from adsorption, we have the concentration of theta C over K adsorption is equal to concentration of cumene times the concentration of the vacant active sites. Simplifying, this is concentration of theta C is equal to K adsorption, concentration of cumene, and concentration of the vacant active sites. For the surface reaction, we have concentration of theta C is equal to concentration of theta B times concentration of propylene over K sub S. We can derive from here the concentration of theta B, that is theta C times capital Ks all over concentration of propylene. Now, to make our lives easier, you can now substitute your concentration of theta C obtained from the previous equation to our equation. Now, we can have K adsorption, K surface reaction, multiplied by the concentration of cumene, multiplied by the concentration of the vacant active sites, divided by the concentration of propylene. And that is our concentration of theta B. Now, same procedure as with the other two iterations, we now have our site balance. And that is theta T is equal to theta vacant plus theta containing cumene plus theta containing benzene. We have the concentration of the total active sites is equal to the concentration of the vacant active sites plus K adsorption, concentration of cumene, concentration of the vacant active sites plus theta B, capital K adsorption, capital K surface reaction, concentration of C, concentration of vacant active sites all over concentration of propylene. Let us extract the concentration of the vacant active sites. This gives us a factor of 1 plus K adsorption, concentration of cumene, plus K adsorption, K surface reaction, concentration of cumene all over concentration of propylene. From this collection of equations, we can now derive our final rate law. So what we will do is we will substitute the definition of theta B into our rate law equation. After that, we can now substitute our derived equation for the concentration of the vacant active sites from the site balance into here and also into here. After that, we should be able to get the rate law considering desorption is the rate limiting step. We now write our net rate of consumption of cumene is equal to small k desorption multiplied by the concentration of active sites containing benzene, that is K adsorption, capital K surface reaction, multiplied by the concentration of cumene, multiplied by the concentration of the vacant active sites, divided by concentration of propylene, minus the concentration of the vacant active sites, concentration of benzene, divided by capital K D. From the previous page of our solution, we have identified that theta V, or the concentration of the vacant active sites, is equal to the concentration of the total active sites divided by 1 plus capital K adsorption, concentration of cumene, plus capital K adsorption, capital K surface reaction, concentration of cumene over concentration of propylene. Factoring out theta V and substituting, we now have the overall rate of consumption of cumene is equal to small kd multiplied by the concentration of the total active sites divided by 1 plus capital K adsorption, concentration of cumene, plus capital K adsorption, capital K reaction, concentration of cumene over concentration of propylene. And that is multiplied to capital K adsorption, capital K reaction, concentration of cumene all over concentration of propylene minus concentration of benzene over equilibrium constant of desorption. From the terms in the parentheses, we can simplify this by having a common denominator. The common denominator is capital KD and the concentration of propylene. We now have the expression capital K adsorption, capital K surface reaction, capital K desorption times the concentration of cumene minus concentration of benzene times the concentration of propylene. Substituting and simplifying, we now have our net rate of consumption of cumene as desorption, concentration of the total active sites multiplied by capital K adsorption, capital K surface reaction, and then capital K desorption, concentration of cumene minus concentration of benzene, concentration of propylene, all over Kd, concentration of propylene, plus K adsorption, K desorption, concentration of cumene and concentration of propylene, plus K adsorption, K surface reaction, K desorption multiplied by the concentration of cumene. This is now our final overall rate law expression for the consumption of cumene if desorption is rate limiting. And there we have it. We have derived three different rate laws for the same catalytic reaction. All we have to do is to choose which one of them is correct. Let me summarize the three rate laws. Here we have a summary of the three rate laws that we have derived, assuming each of these steps as the rate limiting. Let us go back to our presentation. It is mentioned here that at low initial partial pressures of cumene, the initial rate of reaction is observed to be linearly proportional to cumene pressure. Therefore, our rate law has to reduce to a linear equation at low concentrations of cumene. At high initial partial pressures, the initial rate of reaction seems independent of the initial partial pressure. This also indicates that at high initial partial pressures, the initial rate of the reaction seems independent of the initial partial pressure. We are talking here of the initial partial pressure of cumene and the initial rate of reaction. Therefore, all of the terms containing the concentrations of benzene and propylene would have to be removed from our expressions. Let's go back to the board. For our decision-making process, all we have to do is to make a plot wherein our y-axis is the initial rate of reaction, that is initial negative R sub C, and then our x-axis is the initial concentration of cumene. Based on the problem statements, at low concentrations of cumene, the relationship is linear, while for high concentrations, the rate of reaction is independent of the cumene concentration. That looks like a constant function. Therefore, if you have to connect these two parts of the graph, this is the overall behavior of the reaction. It is linear on the low concentration side and it is constant on the high concentration side. Let us now take a look at our equations. First, let us cancel the terms and simplify our equations. Since we are talking about the initial rate of the reaction, the concentrations of the products are all 0. So for our first equation, this is 0, 0, 0. Our equation simplifies to K adsorption, concentration of the total active sites, concentration of cumene. For our second equation, this cancels, this also cancels. We will be left with the expression small ks, concentration of the total active sites, capital K adsorption, concentration of cumene, all over 1 plus K adsorption, concentration of cumene. Finally, if we assume that desorption is the rate limiting step, this cancels, this and this also cancels. As a result of that, we are only left with small kd times the concentration of the total active sites. Now let us judge our three derivative equations. Which among those equations would generate a graph that is similar to what the problem has stated? Let's start with the adsorption. For our first equation, you can see that this is a linear equation. Therefore, when you graph that, regardless of the concentration, the rates will be linear. Let's jump to our third equation. The third equation is independent of the concentration of cumene. Therefore, the rate is constant regardless of the concentration of cumene. That is simply a horizontal line. For our second equation, let us consider both cases of high and low cumene concentrations. If the concentration of cumene is low, that means that 1 is much greater than KAD times the concentration of cumene. Therefore, this second term in the denominator is practically 0. Therefore, at low concentrations, we have a linear relationship. In the same equation, for high concentrations of cumene, we can then say that 1 is much less than the product's K adsorption times the concentration of cumene. Therefore, we can neglect the value of 1 in the denominator, and that would result to the cancellation of the cumene term in the numerator and in the denominator. That leaves us with a constant reaction rates independent of the cumene concentration. And when we connect these two pieces of the graph, we see that this has the same behavior as was described in the problem. Our conclusion here is adsorption is not the rate limiting step. Desorption is also not the rate limiting step. It is surface reaction. Therefore, our rate law is dictated by the middle equation here. This is the rate law that best describes the rate of consumption of cumene for its catalytic decomposition. That is the general method on how we determine the rate law for a catalytic reaction. Keep in mind that we have not yet included the effects of mass transfer. The limitations for mass transfer and its ramifications for the overall rate law will be discussed in the next lesson. To summarize, our approach for these kinds of problems would be is to first assume that adsorption is the rate limiting step, derive the rate law, do the same for surface reaction and desorption, so you would end up with 3 rate laws, and then compare those derived rate laws with experimental observation, such as what we have done here. And from the behavior of the initial rate law with respect to the concentration of the reactant, you can decipher which among the 3 steps is the correct assumption as the rate limiting step. For these types of derivations, you have to keep practicing. You have to master the skill of deriving the rate laws of catalytic reactions. That's it for this lesson. I hope you have learned something. Thank you for listening, and as always, keep safe.